Welcome to the Deep Dive.
Yeah.
We're the place that takes these really complex tech stacks, breaks them down, and gets you the solid foundation you need.
No jargon, just understanding.
Exactly. And today, we're really diving deep, right into the heart of what makes computers fast or, well, not grind to a halt. We're talking about the data cache.
The unsung hero. Absolutely essential.
Our mission here is to really dissect this thing. It's not just a piece of silicon, right? We're looking at the technical analysis, understanding why it's built in layers, how it actually predicts what your software needs.
So it exploits program behavior, yeah.
And this constant battle, this architectural fight to keep it incredibly fast, but also increasingly secure. And, where does it go from here?
And you really can't grasp why caches are designed the way they are without understanding the fundamental problem they solve. Architects call it the memory wall.
The memory wall. Sounds ominous.
It kind of was. Still is in many ways. The whole reason for caching comes down to this massive gap in performance that just, opened up over the decades.
A gap between what and what?
Between processor speed and memory speed. Moore's law meant CPUs got exponentially faster, doubling performance every, 18 months or so?
Something like that, yeah. Insane speeds.
But main memory, the big DRAM chips where all your data lives, its speed only improved marginally, incrementally.
Yeah.
You're limited by physics there, moving charge around distance.
So the processor's roaring ahead, but the memory is lagging way behind. Can you give us a sense of the scale? Like, how big is that difference in real terms?
Okay, let's talk processor cycles. Think of it as the heartbeat of the CPU. A modern processor might do something every quarter of a nanosecond, maybe even faster. Sub-nanosecond stuff.
Okay, incredibly fast.
But asking main memory DRAM for a piece of data, that round trip takes easily 50 to 100 nanoseconds, maybe more.
Wait, nanoseconds sounds small, but compared to sub-nanosecond, how many cycles is the CPU just waiting?
That's the kicker. It translates to hundreds of cycles, like 200, maybe 300 processor cycles just sitting idle, waiting for that data to arrive from DRAM.
300 cycles. The CPU could have done hundreds of operations in that time.
Precisely. That's the memory wall. The processor is starved for data it needs right now, and the main memory just can't deliver it fast enough. The cache is the bridge. It creates this illusion, this trick.
An illusion of memory being both huge, like DRAM, and super fast, like the processor wants.
Exactly. And it pulls off this magic trick by basically gambling, making educated guesses about what data you'll need next.
And these guesses aren't random, right? They're based on how programs tend to behave, these two principles of locality.
Spot on. It all hinges on locality. First, there's temporal locality. Temporal meaning time. If you access a piece of data now,
chances are you'll need it again really soon, like a variable in a loop or something you keep checking.
Perfect example. That's temporal locality. The second one is spatial locality. Space, meaning location, if you access a byte at a particular memory address.
You're probably going to need the bytes right next to it pretty soon, too, like walking through an array or reading fields in a struct.
Exactly that. Or even just fetching the next instruction in sequence. So the cache is designed from the ground up, its structure, its size, its rules. Everything is about exploiting these two predictable behaviors, temporal and spatial locality. That's the secret sauce.
Okay, so let's unpack this system. You called it a bridge, but it's more like a series of bridges, right? This memory hierarchy.
Yeah, hierarchy is the key word. It's not just one cache. It's a layered system built entirely on trade-offs.
Trade-offs between speed, size, and cost. That seems to be the constant theme.
Absolutely. As you go faster, the memory technology gets way more expensive per byte, and physically, you just can't build it as large. So you create layers.
Starting at the very top, closest to the CPU's brain.
That's the registers. They're not even really memory in the traditional sense. They're part of the CPU core itself. Access time? Basically zero weight. Same speed as the CPU clock. But you only have a handful of them. Maybe a few hundred bytes total. Just enough for the current operation.
Okay, lightning fast but tiny. What's the first real cache level then?
That's your L1 cache, level 1. Still incredibly fast, very close to the core. Latency is maybe 3 or 4 processor cycles. Tiny delay.
Still measured in just a few cycles.
Yeah.
But bigger than registers.
A bit bigger, yeah. Typically around 32 kilobytes, maybe 64 kilobytes per core in modern chips. Still quite small, but way larger than registers.
And L1 often has this unique split structure, doesn't it? Separate caches for instructions and data.
It does, yeah. That's a classic Harvard architecture idea applied at the L1 level. It solves a potential bottleneck called a structural conflict.
Meaning?
Well, imagine the CPU needs to fetch the next instruction to execute, and at
Hmm.
the same time, the current instruction needs to load some data from memory if you only have one L1 cache pathway.
They collide. Only one can go at a time.
Right. By splitting L1 into an instruction cache, I cache, and a data cache, D cache, you effectively double the bandwidth at that critical level. They can both access their respective caches simultaneously. Plus, the I cache can be simpler. It mostly just reads, doesn't usually need to handle writes or complex coherence stuff.
Makes sense. Optimize each for its specific job. Okay, so if the data isn't in L1D cache, we take a slightly longer walk
To the L2 cache, level 2. This one is usually unified. It holds both instructions and data. It's bigger than L1, maybe 256 kilobytes up to a megabyte, sometimes more per core.
Bigger means slower, following the trade-off.
Yep. Latency jumps up a bit. Now we're talking maybe 10 to 15 cycles, still very fast compared to main memory, but noticeably slower than L1. L2 catches things that are used fairly often, but maybe not intensely enough or are too big to fit in L1.
And then there's often one more level of cache on the chip itself.
Right, the L3 cache. This one is usually much larger, say 8 megabytes up to 64 megabytes, sometimes even more on server chips. And crucially, it's often shared across multiple or even all cores on the chip.
Shared. So all cores dip into the same L3 pool.
Correct. It acts as a sort of last resort on-chip backstop. If a core misses in its private L1 and L2, it checks the shared L3. It also helps cores communicate, sharing data through that common L3. Latency here is higher again, maybe 40 to 50 cycles.
So registers L1, L2, L3. Only if you miss all of those do you pay that massive penalty we talked about.
That's the one. Only after an L3 miss do you have to go off-chip to the main DRAM, and that's when you face the 200, 300 cycle wait. That whole hierarchy is designed to make that painful trip happen as rarely as possible.
Okay, now let's zoom in. How does data actually move between these layers? It's not byte by byte, right? You mentioned spatial locality.
Right. It moves in fixed-size chunks called cache lines or sometimes cache blocks. The standard size in virtually all modern systems is 64 bytes.
Why 64? Why not 32 or 128?
It's a sweet spot found through decades of experimentation. It's large enough to effectively capture spatial locality if you need byte 8. Grabbing bytes 0 through 63 is a good bet. You'll need some of the neighbors soon.
Mm-hmm.
But it's not so large that you waste bandwidth fetching tons of data you don't end up needing. 64 bytes seems to hit the balance pretty well for typical programs.
So when my program asks for, say, a 4-byte integer, the system actually fetches the entire 64-byte line containing that integer.
Exactly. It brings in the requested data plus its 60-something neighbors, hoping spatial locality pays off.
And just bringing the data isn't enough. The cache line needs some bookkeeping info, some metadata attached to it.
Absolutely crucial. Each 64-byte line carries extra bits. You need the valid bit just tells you if the data in this line is actually meaningful or just leftover garbage. You need a dirty bit, has the CPU modified this data since it was loaded from memory. We'll come back to why that's important. And you need bits for coherent state, especially in multi-core systems, to track who has copies and whether they're up to date.
And critically, you need something to tell you which 64-byte chunk of main memory this line actually represents, the address information.
Right, that's how you find things. When the CPU generates, say, a 64-bit physical memory address, it wants to read or write.
Physical address meaning after any virtual memory translation.
Correct. The actual address in DRAM. The cache hardware logically splits that physical address into 3 pieces.
Okay, break it down for us.
The lowest bits are the offset. Since a cache line is 64 bytes, which is 2 to the power of 6, you need 6 bits to specify which byte within that 64-byte line you actually care about, 0 to 63.
Got it. Selects a byte within the line. What are the next bits up?
Those form the index. The index bits determine which specific location or set within the cache this memory address could possibly reside in. If your cache is organized into, say, 124 sets, you'd need 10 index bits, 210 indent, and 24 to select one of those sets.
So the index points you to a specific row or bucket in the cache, but multiple memory addresses could have the same index bits, right?
Exactly. Many, many different 64-byte blocks from main memory will map to the same set in the cache because their index bits happen to match. That's where the final piece comes in, the tag.
Leftover bits at the top.
All the remaining high-order bits of the physical address form the tag. This tag is stored alongside the data in the cache line. So when you access the cache, you use the index to find the right set. Then within that set, The hardware compares the tag part of the address you're requesting with the tags actually stored in the lines of that set.
So a cache hit only happens if.
If the index selects the set and the tag matches one of the tags stored in that set and the valid bit for that line is turned on, only then do you have a hit and can use the offset to grab the specific bytes you need. If any of that fails, it's a cache miss.
Okay, that tag index offset breakdown naturally leads into how the cache actually decides where a given block of memory can even be placed. The mapping strategy, you mentioned sets, this sounds like it's getting complex.
It is, and the choice here has huge performance implications. There are basically three main ways to do this mapping, representing different trade-offs between complexity and how effectively the cache space is used.
Let's start with the simplest one.
That would be the direct mapped cache, simplest hardware. In this scheme, any given block of memory, based on its index bits, can only go into one specific location in the cache. Period. There's no choice.
So memory address X always maps to cache line Y. Always.
Exactly. When the CPU requests address X, the hardware uses the index bits to go directly to line Y, checks the tag, and that's it. Very fast check, very simple hardware.
Sounds efficient. What's the catch? It feels like there has to be a catch.
Oh, there's a big one. Conflict misses. Imagine your program is actively using two different pieces of data, say data A and data B, whose addresses just happen to have the same index bits.
So they both map to the exact same single cache line, line Y.
Right. What happens? You load data A, it goes into line Y. Then you need data B. You load data B, it kicks out data A and takes its place in line Y. Then you need data A again.
You kick out data B. They just keep evicting each other, back and forth, back and forth.
Even if the entire rest of the cache is completely empty and unused, it's incredibly inefficient if you hit that conflict pattern. Performance can absolutely tank because of these conflict misses in a direct mapped cache.
Okay, that's clearly not ideal for performance. So what's the opposite extreme? Maximum flexibility.
That's the fully associative cache. Here, a block of memory can be placed anywhere in the cache. There are no sets, no index bits used for placement. Any line can hold any memory block.
Total freedom. It sounds like it would solve the conflict miss problem completely.
It does. Conflict misses are eliminated. The cache can always find space if there's any free line, regardless of address patterns. It gives the best possible cache utilization in theory.
But, and here comes the trade-off again. Why aren't all caches fully associative then? The hardware must be gnarly.
Extremely gnarly and expensive. Think about it. If a memory block can be anywhere, how do you find it? When the CPU requests an address, the hardware has to compare the tag of that address against the tag stored in every single line of the entire cache, all at the same time, in parallel.
For a large cache, say L3, with millions of lines, comparing against all of them simultaneously.
You need millions of comparators consuming huge amounts of power and silicon area. It's just not feasible for large caches. So full associativity is usually only used for very small, very critical structures where the cost is justified, like maybe a TLB or a tiny victim cache where you have maybe tens or hundreds of entries, not hundreds of thousands.
Okay, so direct map is simple but prone to conflicts. Fully associative is flexible, but way too complex for big caches. There must be a middle ground.
And that's exactly what virtually all modern L1 and L2 caches use, the set associative cache. It's the practical, effective compromise.
How does it work? It sounds like a hybrid.
It is. The cache is divided into sets determined by the index bits, just like a direct mapped cache. But each set doesn't contain just one cache line. It contains multiple lines, say n lines. N is the associativity, or the number of ways.
So you might have an 8-way set associative cache.
Exactly. That means a memory block, based on its index, maps to a specific set. But once it gets to that set, it can be placed in any of the 8 available lines or ways within that set.
Ah, so you still use the index to narrow down the location quickly, but then you have some flexibility within that set.
Precisely. When you search, you use the index to select the set, and then you only need to compare the tag against the n tags, say 8 tags, within that set in parallel.
Yeah.
Much more manageable than comparing against the entire cache.
And having, say, 8 slots instead of just one significantly reduces the chance of those conflicts we talked about.
Dramatically reduces them. It's not perfect. You can still have a conflict if you have, say, 9 active blocks mapping to the same 8-way set, but it's a massive improvement over direct mapped without the insane cost of full associativity. Most modern caches are somewhere between 4-way and 16-way set associative.
Okay, so set associativity gives us placement flexibility. But now, if a set is full, all n ways have valid data, and we need to bring in a new block that maps to that same set, we have a problem. We have to kick something out.
We need an eviction strategy, a replacement policy. We need to choose which of the end lines in the set is the victim that gets thrown out to make space for the new arrival.
What's the smartest way to choose the victim? What's the ideal policy?
The policy generally considered to give the best performance, the one we try to approximate, is least recently used, LRU.
Least recently used. So kick out the line in the set that hasn't been touched for the longest time.
Exactly. The logic is, if it hasn't been used in a while, it's probably the least likely to be needed again soon. It tries to preserve the data with the best temporal locality.
Makes sense intuitively. But tracking the exact usage order of, say, all 16 lines in a set sounds complicated, especially at high speed.
It's very complicated in hardware. To implement true LRU, every time any line in the set is accessed, you potentially have to update the recency information for all lines in that set to maintain the perfect order. That takes complex logic, extra storage bits for timestamps or counters, and time potentially adding latency to every cache hit. It's often just too expensive for high associativity caches.
So if true LRU is too costly, what do we do instead?
Approximate.
We approximate it. The most common approach is pseudo-LRU, PLRU. There are various PLRU algorithms,
Right.
but they all aim to get close to LRU performance with much simpler hardware, often using just a few extra bits per set to maintain an approximate order.
Like a binary tree structure or something.
Yeah, tree-based PLRU is common. For an 8-way set, you might only need 7 bits to track the state, and updating it is much faster than true LRU. And the performance difference is usually very small in practice. It's a very good trade-off.
Are there even simpler options?
You could go really simple with random replacement. Just pick one of the end lines in the set at random and evict it.
Random, that sounds like it would perform terribly.
You'd think so. But counterintuitively, for caches with high associativity, like 16-way or more, random performs surprisingly well. Not quite as good as LRU or PLRU, but often close enough, and the hardware cost is absolutely minimal. Just need a random number generator. So you sometimes see it, especially in L3 caches where minimizing complexity is key. Okay, one last policy. You mentioned this when we discussed benchmarking. Ability's optimal.
Ah, yes. Validity's optimal policy. This is purely theoretical. It's the perfect replacement policy. It says, evict the cache line whose next access will be furthest in the future.
Furthest. Wait, that would require knowing the future.
Exactly.
Yeah.
You'd need a crystal ball. It's impossible to implement in a real system. Its only value is as an offline analysis tool. Researchers simulate Bility's policy on memory access traces to establish the absolute best possible miss rate for a given cache size and associativity.
So it's the theoretical ceiling. You compare your real-world PLRU or random policy against Bility's to see how much performance you're leaving on the table compared to perfect foresight.
Precisely. It tells you the limits of what any replacement policy could possibly achieve.
All right, we've got the structure, the mapping, the replacement. Now, how do we actually measure if this whole complex dance is working well? We need performance metrics.
Yeah, we need to quantify success. The most basic metrics are the hit rate and the miss rate. Hit rate is the percentage of memory accesses that are found in the cache. Miss rate is the percentage that are not found and have to go to a lower, slower level.
So higher hit rate, lower miss rate is obviously better.
Generally, yes. But just looking at the miss rate alone can be misleading. A 5% miss rate sounds good, right? But what is the cost of those misses?
Because missing in L1 is way less painful than missing in L3 and having to go to DRAM.
Exactly. That's why the most important single metric is usually the average memory access time, AMAT.
Okay, how's that calculated?
The basic formula is AMAT hit time plus miss rate x miss penalty.
Hit time plus miss rate x miss penalty. Let's break that down. Hit time is
The time it takes to access the cache if the data is there. For L1, that's maybe 3 first cycles. Very fast.
miss rate is the percentage we just talked about, like 0.05 for a 5% miss rate.
Right. And the miss penalty is the extra time it takes to get the data from the next lower level in the hierarchy if you miss at the current level.
So the penalty for an L1 miss isn't the full DRAM access time.
No. The penalty for an L1 miss is the time it takes to access the L2 cache. Let's say that's 12 cycles. So L1 AMAT equals L1 hit time plus L1 miss rate s L2 access time.
And the L2 access time itself depends on the L2's hit rate and the L3 access time as its penalty.
It nests. It nests all the way down. The miss penalty for L2 is the L3 access time. The miss penalty for L3 is the main memory access time, that huge 200, 300 cycles. This formula really highlights how devastating misses are, especially at higher levels, because the penalty gets multiplied by the miss rate at each step. Reducing that miss rate, especially in L1, L2, is critical.
Okay, AMAT gives us the overall picture. But to actually improve things, we need to know why misses are happening. This leads to the famous 3 Cs of cache misses, right?
Yes, pioneered by Mark Hill and David Patterson. It's a fundamental way to classify misses to understand the root cause. The first type is the compulsory miss, sometimes called a cold miss.
Compulsory, meaning unavoidable.
Pretty much. This is the miss that happens the very first time a program ever accesses a specific block of memory. It's not in any cache yet, so you have to go fetch it from main memory. It's a cold start for that block.
Can you do anything about compulsory misses? Seems like you just have to pay the price once.
You can eliminate them, but you can hide their latency. That's where prefetching comes in. If the hardware or software can guess ahead of time that you're going to need a block, it can start fetching it before the actual request, if the prefetch completes in time.
The compulsory miss turns into a hit, or at least the penalty is reduced.
Exactly. Prefetching is the main weapon against compulsory misses.
Okay, what's the second C?
Capacity misses. These happen simply because the cache isn't big enough to hold all the data the program is actively using at that moment. Your working set of data exceeds the cache's capacity.
So even if you had a fully associative cache with a perfect LRU policy, you'd still get these misses if your program needs 10 MB of data, but your cache is only 8 MB.
Precisely. Data gets loaded, but because the cache is full, other necessary data has to be evicted. Later, when you need the evicted data again, you miss. The only way to reduce capacity misses is fundamentally
Make the cache bigger, which costs more money and potentially slows down hit time. The trade-off, again.
always the trade-off.
And the third C, this relates back to mapping strategies.
Conflict misses, also called collision misses. These are the ones we discussed with direct mapped caches, but they can happen in set associative caches too, just less often. A conflict miss occurs when a block has to be evicted because too many other blocks map to the same set, even though there might be plenty of empty space in other sets of the cache.
So the total capacity is fine, but the specific set you need is overloaded due to the mapping function.
Right. It's an artifact of the limited associativity. The main way to reduce conflict misses is to
Increase the associativity.
Yeah.
Go from 4-way to 8-way or 8-way to 16-way. More choices within the set.
Correct. More ways means fewer conflicts.
So compulsory, capacity, conflict. Those are the big three. But you hear people talk about a fourth C sometimes, especially in multi-core systems.
Yes, that's the coherence miss. This one isn't about first access, size, or mapping conflicts within a single core's view. It happens purely because of communication between cores.
How does that work?
Imagine Core A has a copy of data X in its cache. Core B also has a copy. Now, Core B writes to data X. To maintain consistency, the cache coherence protocol has to tell Core A, hey, your copy of X is now stale, don't use it. It invalidates Core A's line.
So later, when Core A tries to read X,
It finds its line marked invalid. That's a coherence miss. It has to go fetch the updated version, maybe from Core B's cache or from memory. It's a miss caused entirely by another processor's activity. We'll get deeper into coherence soon.
got it. Beyond the Cs, are there other metrics engineers track day-to-day for tuning?
Definitely. Raw miss rate can fluctuate a lot depending on the program phase. A more stable metric often used is misses per kilo instruction, MPKI, or sometimes misses per instruction, MPI.
So how many misses happen for every 1,000 or 1 instructions the CPU executes?
Right. It normalizes the misbehavior relative to how much work the CPU is actually doing. A high MPKI signals that the memory system is really struggling to keep up with the processor's demands, regardless of the absolute miss rate. It's a key indicator of memory bottleneck.
And one more, MLP.
Memory level parallelism, MLP. This measures how many cache misses can be in flight or being serviced simultaneously without stalling the processor pipeline. Modern out-of-order processors try to overlap the latency of multiple misses.
So if a processor can handle, say, 4 misses at the same time, continuing to execute other independent instructions while waiting.
It has an MLP of 4. Higher MLP is crucial for hiding that miss latency. It depends on features like non-blocking caches and enough internal buffers like MSHRs, which we'll get to track those outstanding requests.
Okay, we've focused a lot on reading data from the cache. But what happens when the CPU writes data, modifying it? This seems like it adds a whole new layer of complexity, especially keeping things consistent with main memory.
It absolutely does. The core decision is the right policy. When does a modification made in the cache actually get written back to the slower main memory?
What's the simplest approach?
Conceptually simplest is write through. Every time the CPU performs a write operation that hits in the cache, the data is updated in the cache and simultaneously written through to the next level down. L2, or eventually main memory.
So main memory is always kept perfectly up to date.
Exactly. That simplifies things like coherence, because the true value is always in memory. But the downside is
Massive traffic. If you're writing frequently, you're constantly hitting that slow memory bus.
huge amounts of bus traffic. Imagine a loop incrementing a counter 100 times. That's 100 separate write transactions going down the hierarchy. It would completely bottleneck the system.
How do systems using write-through cope with that? They must have some way to avoid stalling the CPU on every write.
They rely heavily on write buffers. These are small, fast FIFO queues sitting between the cache and the next level. When the CPU writes, the data goes into the cache and gets put into the write buffer immediately. The CPU can then continue executing its next instruction right away.
And the write buffer drains itself out to main memory in the background when the bus is free.
Precisely. It decouples the CPU from the slow write latency, but you still generate all that traffic eventually, and the write buffer itself can fill up under heavy load, causing stalls.
Okay, so write-through is simple but traffic-heavy. What's the alternative? Presumably used in performance-critical caches like L1, L2.
That's write back. This is much more common for high-performance caches. When the CPU writes to a line in a write-back cache, the change is made only in the cache line itself.
Only in the cache, not written to memory immediately.
Not immediately. Instead, that dirty bit metadata we mentioned earlier gets set for that cache line. This dirty flag indicates that the cache holds a modified version that is newer than what's in main memory.
So main memory is now holding stale data. When does it get updated?
Only when that dirty cache line is eventually chosen as a victim and needs to be evicted, for example, by the replacement policy to make space for something else. Before overwriting the dirty line with new data, the cache controller first writes its contents back to main memory.
Ah, so writes happen in bulk, only on eviction. That must save a ton of traffic compared to write-through.
Dramatically less traffic. Multiple writes to the same line only result in one final write back when it's evicted. But the complexity is higher, right? Because now main memory isn't the single source of truth anymore. The latest data might be sitting in some cache marked dirty.
Which sounds like it's going to make multiprocessor coherence much harder.
Bingo. We'll see that in a moment.
One more write detail. What happens on a write miss? If the CPU tries to write to an address that isn't currently in the cache.
Good question. There's another policy choice here. Write allocation, sometimes called fetch on write versus no write allocate, right around.
Okay, write allocate.
With write allocate on a write miss, the system first reads the entire 64-byte block from memory into the cache, then performs the write operation on that newly loaded cache line and marks it dirty, assuming write back.
Why read the whole block if you're just going to overwrite part of it?
To exploit locality. The bet is that after writing to this byte, you'll likely read or write other bytes in the same block soon. So bring the whole block in now to turn those subsequent accesses into hits. Write allocate is almost always paired with write back caches.
And the alternative, no write allocate.
With no write allocate on a write miss, the write operation bypasses the cache entirely and goes directly to the next level down, for example, L2 or main memory. The block is not loaded into the cache where the miss occurred.
When would you use that? Seems like you lose locality benefits.
It's typically paired with write-through caches. The idea is if you're writing through anyway, maybe avoid polluting the cache with data you might only write once and never read again, like initializing a large buffer. But write back, write allocate is a much more common combination for performance.
Okay, now we have to tackle the elephant in the room. Multiple processors. As soon as you have Core 0 and Core 1, each with its own L1, L2 caches, maybe holding copies of the same memory location, how do you keep things consistent? This is the cache coherence problem.
This is arguably one of the most complex parts of modern processor design. If Core 0 reads address A, gets a value of 10, then Core 1 reads address A, gets 10. Now Core 0 writes 20 to address A in its local cache. What happens when Core 1 tries to read A again?
It better not read the old value of 10 from its local cache. It needs to see the 20 somehow.
Exactly. That's the essence of coherence. We need to ensure that all processors have a consistent, unified view of memory, even though there are multiple private copies floating around in caches. There are two fundamental properties we need.
What are they?
First, write propagation. A write by one processor must eventually become visible to all other processors. The value 20 has to propagate. Second, write serialization. All processors must observe writes to the same memory location in the same order. If Core 0 writes 20, then Core 1 writes 30, everyone has to agree that the final value is 30, not potentially see the writes out of order.
How do systems enforce this? Especially in smaller systems, say up to a few dozen cores, where they might share a common bus.
On systems with a shared bus, or a shared L3 acting like a bus, the dominant approach is using snooping protocols. Every cache controller snoops or monitors the bus traffic. When one cache needs to perform an operation that might affect others, like a write, it broadcasts its intention on the bus.
And the other caches listen in and react if they have a copy of the data involved.
Precisely. They check the address on the bus against their own tags. If they have a match, they might need to update their state or provide data. The simplest snooping protocol is MSI.
MSI. What does the letter stand for?
The three possible states a cache line can be in: modified M, shared S, or invalid I.
Okay, walk us through them.
Invalid I is easy. This cache line doesn't hold valid data. Ignore it. Shared S means this cache holds a clean, unmodified copy of the data, and other caches might also hold clean copies. You can read from a shared line freely. Modified M means this cache holds the only valid copy, and it's dirty, it has been modified locally, and memory is stale.
So if a cache wants to write to a line that's currently in the shared S state,
It can't just write. Other caches might have shared copies. So it must first broadcast an invalidate message on the bus for that address. All other caches snooping the bus see the invalidate, check if they have the line, and if so, mark their copy as invalid. Only after the invalidation is acknowledged can the original cache perform the write and transition its state to modified M.
that seems okay. But what if only one cache had the line in shared state? Does it still need to broadcast the invalidate?
In basic MSI, yes, it doesn't know if anyone else is sharing. That inefficiency led to the most common enhancement, the MEDISI protocol.
MEDISI adds an E. What's E?
Exclusive E. This state represents a line that is clean, matches memory, and this cache is the only cache holding a copy.
Ah, so it knows it has exclusive ownership even though it's clean? How does that help?
It's a huge performance win for writes. If a cache holds a line in the exclusive E state and the CPU wants to write to it, the cache knows no other cache has a copy. Therefore, it can just write locally and transition the state directly from E to modified M without sending any message on the bus at all.
Nice. Silent write. Upgrade. Avoids that costly bus transaction.
The big improvement. MENSI is the foundation for most modern coherence protocols.
Is there anything beyond MESSI? I think I've seen MOEC mentioned.
Yes, MOEC adds one more state, owned, O. This one gets a bit more complex. The owned state allows a cache line to be shared. Other caches have copies, but also dirty. This cache holds the most recent value and memory is stale.
Wait, shared and dirty. How does that work?
The owner cache, the one in the O state, takes responsibility. If another cache requests the data, for your example, on a read miss, the owner cache directly supplies the data to the requester, cache to cache, without having to write it back to main memory first.
So it satisfies read requests for dirty data from its cache, avoiding the slow trip to DRAM.
Exactly. It optimizes sharing of frequently written data, allowing faster cache-to-cache transfers. MOEC adds complexity, but can improve performance in specific sharing patterns.
Okay, so MSI, MEAN-SI, MOEC work by snooping on a shared bus. But you mentioned this doesn't scale well. What happens in really big systems like supercomputers or large servers with hundreds of cores, that bus would be overwhelmed.
Totally overwhelmed. Broadcasting every coherence message to hundreds of snooping caches is just not feasible. The bandwidth requirements explode. For large-scale systems, you have to move away from snooping to directory-based coherence.
Directory-based. How does that avoid the broadcast storm?
Instead of broadcasting, there's a directory. This directory structure, which might be centralized or distributed across the system, keeps track of the state of every cacheable memory block. Crucially, for each block, it knows which specific processors currently have a copy of it.
It maintains a list, like a sharing vector.
Exactly, a sharing vector or pointer list. So when a processor wants to write to a block currently marked as shared in the directory controller looks up the sharing vector and sends targeted point-to-point invalidation messages only to those specific caches that actually hold a copy.
No broadcast needed, just targeted messages.
Right. This dramatically reduces the coherence traffic on the interconnect network, allowing the system to scale to hundreds or even thousands of cores where snooping would completely break down. The trade-off is the extra storage needed for the directory itself and the latency of directory lookups. So we've got coherence sorted, more or less, but we still have that fundamental problem. Misses happen, and DRAM is slow. Even with caches, that 200, 300 cycle penalty looms. A huge part of modern CPU design is dedicated to latency hiding, making the processor feel faster even when it's stuck waiting for memory.
Trying to keep the execution units busy doing something useful during a miss instead of just stalling.
Exactly. And the most proactive way to do that is prefetching. We touched on it briefly with compulsory misses. The idea is to predict what data the program will need in the future and start loading it into the cache before the CPU actually asks for it.
If the prediction is right and the data arrives on time.
What would have been a cache miss becomes a cache hit, or at least the wait time is significantly reduced because the fetch was already in progress.
How do systems make these predictions? Is it magic?
Not quite magic, but clever heuristics. There are two main flavors: hardware prefetching and software prefetching.
Software prefetching means the programmer or compiler puts hints in the code.
Right. You insert special prefetch instructions that tell the hardware, hey, I'm probably going to need the data at this address soon, maybe start fetching it. This can be very precise if the programmer knows the access patterns well, but it requires manual effort or sophisticated compiler analysis.
And hardware prefetching works automatically.
Yeah, the hardware monitors the memory access patterns generated by the CPU and tries to detect simple, predictable sequences. The most common type is stride prefetching.
Stride, like the distance between accesses.
Exactly. If the hardware sees accesses to addresses A, then A plus 64, then A plus 128. It detects a constant stride of 64 bytes, the size of a cache line. It then predicts the next access will be to A plus 192 and proactively issues a fetch for that line.
Perfect for loops stepping through arrays.
Works great for that. There are also stream buffers, which are basically small dedicated FIFOs that just fetch consecutive cache lines ahead of the current demand, assuming sequential access. And even more complex schemes like correlation prefetchers that try to learn relationships between accesses to different addresses.
But prefetching sounds like a gamble. What if you predict wrong?
That's the big risk. If you prefetch data that the program never actually uses, you've wasted memory bandwidth fetching it, and maybe even worse.
You could kick useful data out of the cache to make room for the useless prefetched data.
Exactly. That's called cache pollution. Aggressive prefetching can actually hurt performance if it pollutes the cache too much. Designing good hardware prefetchers is a balancing act. Be aggressive enough to hide latency, but not so aggressive that you waste bandwidth and pollute the cache. It's tricky.
Okay, prefetching tries to get data early. What about handling misses when they do happen? Older systems used to just freeze, right?
Yeah, early caches were often blocking caches. If the CPU missed in the cache, the entire processor pipeline would just stall, freeze in place, until the data arrived from memory, potentially hundreds of cycles later. Terribly inefficient.
So the breakthrough was.
Non-blocking caches, also called lockup-free caches. This was a revolutionary idea. When a miss occurs, the cache records the misinformation, starts the fetch from the lower level, but allows the processor to continue executing subsequent instructions as long as those instructions don't depend on the missing data.
So the pipeline keeps moving on independent work.
Right. If the next instruction needs the result of the miss, it will stall. But other independent instruction streams can continue making progress. This allows the processor to overlap the latency of the miss with usable computation.
But how does the hardware keep track of all this? If you have multiple misses happening at the same time for different instructions,
Yeah.
it sounds chaotic.
It requires dedicated hardware structures. The key components are miss status holding registers, or MSHRs. Think of them as little tracking buffers. When a miss occurs, an MSHR is allocated to record the address that missed, where the data should eventually go in the cache, and which instructions in the pipeline are waiting for it.
So each MSHR tracks one outstanding miss.
Essentially, yes. The number of MSHRs available in the cache controller directly determines the maximum memory level parallelism (MLP) the processor can support. If you have 16 MSHRs, you can potentially have 16 cache misses in flight simultaneously. The MSHRs manage merging requests to the same line and ensuring data gets delivered to the right waiting instructions when it finally arrives. Non-blocking caches and MSHRs are absolutely fundamental to modern out-of-order processor performance.
Let's talk about some more specific architectural tricks. I remember reading about victim caches. What problem do they solve?
Victim caches are a clever way to fight conflict misses, especially in L1 caches, which might have lower associativity to keep hit times fast. A victim cache is a small, typically fully associative buffer that sits between the L1 and L2 caches.
Small and fully associative, what does it hold?
It holds the cache lines that were most recently evicted from the L1 cache, the victims of the L1 replacement policy.
Why hold on to the recently evicted stuff?
Think about that direct mapped conflict miss scenario. Data A and data B keep kicking each other out of the same L1 line. When data B kicks out data A, where does data A go? into the victim cache. If the CPU immediately asks for data A again, which is likely in that conflict pattern.
It checks the victim cache first before going to the slower L2.
Exactly. If it finds data A in the victim cache, which is very fast to check since it's small and fully associative, it can quickly swap data A back into the L1, maybe swapping B out into the victim cache. This turns what would have been an L2 access 10-15 cycles into a much faster victim cache hit, maybe just 1-2 extra cycles.
So it gives you some of the benefits of higher associativity for recently used conflicting lines, without making the whole L1 cache more complex. Clever.
Very clever and effective for reducing L1 conflict misses with minimal hardware cost.
Okay, shifting gears back to multi-core. We talked about shared L3 caches. What happens if one core is just a memory hog and fills up the entire shared cache, starving the other cores?
That's a huge problem in multi-core systems, especially servers running diverse workloads. It's called destructive interference. One badly behaved thread or VM can ruin the cache performance for everyone else sharing that resource. This necessitates cache partitioning.
Partitioning, like building walls within the shared cache.
Sort of, yeah. Architects have developed ways to divide up the shared cache resources of like L3 among the different cores or groups of cores to provide some level of isolation and quality of service.
How do they do that?
Several techniques exist. Way partitioning is common. You assign each core or group exclusive access to certain ways within each set of the set associative cache. So core 0 might only be allowed to use ways 0-3, while core 1 gets ways 4-7 in every set. They can't kick each other out of their assigned ways.
So they each get a guaranteed slice of the cache capacity.
Exactly. Another approach is set partitioning, where you might assign different ranges of cache sets based on index to different cores. There are also more dynamic utility-based partitioning schemes that try to monitor cache usage and allocate resources based on which threads benefit most.
Is this something the hardware just does automatically?
Sometimes there are hardware defaults, but increasingly, especially in data centers, this has become programmable. Technologies like Intel's CAA, cache allocation technology, allow the operating system or hypervisor software to control how the shared L3 cache is partitioned.
So the cloud provider can say, okay, this premium customer's VM gets a guaranteed 8 MB slice of the L3, while this background task only gets 2 MB.
Precisely. It allows for performance isolation, predictable performance for critical applications, and prevents noisy neighbor problems in shared environments. Cache partitioning is essential for managing shared resources effectively in modern multi-tenant systems. This drive for performance hasn't just led to partitioning, it's led to more specialization within the memory hierarchy itself. We already talked about the split L1 instruction and data caches. That's specialization 101.
Right, optimizing the I cache just for fetching code sequentially, keeping it simple and fast, separate from the more complex D cache that handles reads, writes, and coherence.
But there's another hugely important specialized cache we haven't really dug into yet, and it's critical for performance. It doesn't cache program data, but rather addresses the translation look-aside buffer, or TLB.
Ah, the TLB. This caches the mappings from virtual memory addresses, which programs use, to the actual physical memory addresses the hardware needs, right? Those page table entries.
Exactly. Modern operating systems use virtual memory, giving each program its own private address space. But accessing actual DRAM requires the physical address. The mapping is stored in data structures called page tables in main memory. Walking these page tables to find the physical address for every single memory access would be incredibly slow.
So the TLB acts as a cache, specifically for those virtual to physical address translations stored in the page table entries, PTEs.
Correct. It's usually a small, very fast, often fully associative or highly associative cache. When the CPU generates a virtual address, it first checks the TLB. If the translation, the PTD, is found there, a TLB hit, the physical address is available almost immediately.
And if it's a TLB miss?
Ouch. A TLB miss is really painful. The hardware has to perform a page table walk. This involves multiple dependent reads from main memory, potentially 2, 3, or even 4 separate DRAM accesses, just to navigate the page table structure and find the correct PTE. Each of those accesses takes that 200-300 cycle penalty.
So a single TLB miss can cost like 1,000 cycles before you even start fetching the actual data you wanted.
Easily. TLB misses are performance killers. That's why TLBs, like data caches, often have their own hierarchy. A small, fast L1 DTLB, data TLB, and maybe a larger L2 TLB.
And this is also why operating systems and applications sometimes use large pages, right, instead of the standard 4 KB page size.
Absolutely critical technique. If you use, say, 2 MB pages or even 1 GB pages, sometimes called huge pages, then a single entry in the TLB covers a much larger chunk of memory.
Meaning you need fewer TLB entries overall to cover the same amount of actively used memory.
Exactly. It drastically reduces the probability of a TLB miss, minimizing those incredibly expensive page walks. Using large pages is a key optimization for workloads with large memory footprints, like databases or scientific computing.
Okay, so the hardware is specialized. But this is a two-way street. Software needs to be aware of the cache architecture to get maximum performance. Programmers can't just ignore it.
Definitely not. If you write cache-oblivious code in the naive sense, you might get functionally correct results, but your performance could be terrible because you're constantly causing cache misses unnecessarily.
What's the classic example of coding for the cache?
The textbook example is cache blocking, sometimes called tiling. It's especially important for algorithms that process large data sets with potentially poor reuse if done naively, like matrix multiplication.
Explain the problem with naive matrix multiplication.
In the simple three-nested loops approach, C equals AB, you might read an entire row of A, then an entire column of B. If the matrices are large, by the time you need that row of A again for the next element of C, it's long gone from the L1 or even L2 cache. You end up reloading the same data over and over from slower memory.
So cache blocking tiling changes the access pattern.
It does. Instead of processing entire rows and columns, you break the matrices down into smaller square blocks or tiles. You load one block of A and one block of B into the cache, perform all the partial multiplications needed between those two blocks to update a corresponding block of C, and then move on to the next pair of blocks.
The key is that the blocks are sized to fit comfortably within a specific cache level, like L1 or L2.
Exactly. You choose a block size, say 32 by 32 elements, such that 2 blocks of input and 1 block of output stay resident in the cache. This maximizes the reuse of the data you loaded. You hit the cache repeatedly for the elements within the block before moving on.
And the speedup can be significant.
Huge. Orders of magnitude, often. It dramatically reduces the number of accesses that have to go to slower memory levels. Tiling is a fundamental optimization technique in high-performance computing libraries like BLA.
Tiling requires knowing the cache size to pick the right block size, though. Is there a way to get good cache performance without knowing the specifics of the hardware?
There is, and it's a really elegant algorithmic idea, cache-oblivious algorithms.
Oblivious,
Yeah.
meaning they don't need to know cache parameters. How does that work?
They typically use a recursive structure. They divide the problem, like matrix multiplication or FFT or sorting, into smaller subproblems. Then they recursively solve those subproblems. The recursion continues until the subproblem's data naturally becomes small enough to fit into whatever cache level it encounters first.
Ah, so the recursion automatically adapts the working set size to the available cache without explicitly being programmed for L1 versus L2 versus L3 sizes.
Precisely. As the recursion unwinds, it naturally reuses data that's still hot in the cache from the deeper recursive calls. These algorithms can achieve asymptotically optimal cache performance across all levels of the memory hierarchy simultaneously without needing any tuning parameters like block size. It's a very powerful concept.
Very cool. Okay, one last code level issue, especially relevant for multi-threaded programming. We talked about coherence misses. What about false sharing?
False sharing is a nasty, subtle performance bug that can bite you hard in parallel code. It happens when two different threads are accessing and modifying different variables.
Completely independent data, they think.
Right, but unfortunately, those two independent variables happen to reside within the same 64-byte cache line.
Oh no, because coherence protocols work at the granularity of a cache line, not individual bytes.
Exactly. So thread A writes to its variable vara. This marks the entire cache line as modified in core A's cache. The coherence protocol might invalidate the copy of that line in core B's cache, even though core B only cares about varb on that same line.
Then thread B wants to write to its variable vara. Its line is invalid, so it has to fetch the line from core A.
Correct. Then thread B writes var, marking the line modified in core B's cache and invalidating core A's copy. Then thread A needs var again.
Ping pong. The cache line bounces back and forth between the cores constantly, even though the threads are accessing logically independent data.
Massive amounts of unnecessary coherence traffic and contention. It looks like the threads are fighting over a shared lock, but they're not. It's purely an artifact of memory layout hitting the cache line boundary. Performance craters.
How do you fix false sharing?
You have to be mindful of data layout. The common techniques are padding and alignment. You might add unused dummy variables, padding, into your data structure, between variables accessed by different threads to force them onto separate cache lines. Or you use compiler directives or memory allocators that align your data structures explicitly to cache line boundaries. Virgin ensure each thread's critical data starts on a 64-byte boundary. It requires careful thought during development.
We spent all this time talking about making caches faster, optimizing them. But it turns out this relentless pursuit of speed created a huge blind spot. The very mechanisms that make caches work opened up massive security vulnerabilities.
It's a classic case of unintended consequences. The fact that a cache hit is measurably faster than a cache missy. The core principle of caching created an information leak, a timing side channel.
An attacker can literally time memory accesses to figure out secret information.
In many scenarios, yes. By carefully observing the timing variations caused by cache hits and misses in a victim process, an attacker running on the same machine, or sometimes even remotely, can infer things about the victim's data or control flow.
What are some of the well-known techniques for doing this? The names sound like spy movie plots.
They kind of do. Two foundational ones are flush plus reload and prime plus probe.
Okay, flush plus reload.
The attacker uses a special CPU instruction, like clay flush on byte 86, to explicitly flush a specific memory address from all levels of the cache hierarchy. Then, they wait for the victim program to run for a short period. After the victim runs, the attacker tries to reload that same memory address.
And times how long the reload takes.
Exactly. If the reload is fast, cache hit, it means the victim must have accessed that address, pulling it back into the cache. If the reload is slow, a cache miss, the victim didn't touch it. By repeatedly flushing and reloading different addresses that might hold sensitive data, like crypto keys, the attacker can leak information bit by bit.
Wow. And prime plus probe.
Prime plus probe works on set associative caches. The attacker first primes one or more cache sets by filling them entirely with their own data. Then the victim runs. If the victim accesses memory locations that map to those same primed cache sets,
the victim's data will evict the attacker's data from those sets.
right. After the victim runs, the attacker probes by measuring the time it takes to reload their own priming data. If reloading data in a specific set is now slow, it means the victim must have accessed something mapping to that set, causing evictions. This leaks information about the victim's memory access patterns, which can again be used to infer secrets.
These sound bad enough, but then came the bombshells in 2018, Spectre and Meltdown. These seem different, somehow worse.
They were worse because they combined cache timing side channels with another major performance optimization, speculative execution.
Speculative execution. That's where the CPU guesses which way a program branch will go and starts executing instructions down that path before it knows if the guess was right.
Correct. If the guess was right, great, you save time. If it was wrong, the CPU is supposed to discard the results of the wrongly executed instructions and roll back its state as if they never happened.
But Spectre and Meltdown show the rollback wasn't perfect.
Exactly. While the architectural state, register values, memory contents, was correctly rolled back, the microarchitectural side effects were not always undone. Specifically, the speculative execution could still leave traces in the cache.
So even if the CPU discarded the result of a speculatively executed instruction that shouldn't have run, like accessing forbidden kernel memory, that instruction might have still loaded the forbidden data into the L1 cache before the rollback happened.
Precisely the problem Meltdown exploited. An attacker could trick the CPU into speculatively executing code that read kernel memory. That read would fault and roll back, but not before the kernel data was briefly loaded into the L1 cache. The attacker could then use a cache timing attack, like flush plus reload, to detect which address got cached, thereby leaking the secret kernel data across the user kernel security boundary. Spectre used similar principles to trick programs into leaking their own data via speculative execution down predicted but incorrect paths.
That's terrifying, breaking fundamental OS protections through performance optimizations. What have processor vendors and software developers done to defend against this?
It's been a massive, ongoing effort involving hardware changes, microcode updates, compiler changes, and OS patches. Defenses include things like strengthening isolation between processes, adding speculative execution barriers like special fence instructions to prevent sensitive data from being accessed speculatively.
Slowing things down deliberately at critical points.
Yes. Other defenses try to break the timing channel itself, like randomized cache indexing, making it harder for prime plus probe attackers to target specific sets, or adding noise to timing measurements. On the software side, Developers of security-sensitive code, especially crypto libraries, now have to write constant-time algorithms.
Constant time, meaning the code takes the exact same amount of time and performs the exact same sequence of memory accesses regardless of the secret input.
Exactly. No data-dependent branches, no data-dependent memory lookups. This eliminates the timing variations that side-channel attacks rely on. It's often much harder to write constant-time code, though.
But all these fixes, they must come at a performance cost, right? Undoing decades of optimization.
Absolutely. There's no free lunch here. The mitigations for Spectre, Meltdown, and related vulnerabilities have had a measurable performance impact. Depending on the specific workload, especially those heavy on context switches, system calls, or with high branch misprediction rates, performance regressions of 5% to 30% have been widely reported after applying the necessary patches.
Wow, 30%. That's a huge hit. It really highlights the tension between performance and security in modern hardware design.
It's a central challenge now. How do we keep pushing performance boundaries without inadvertently creating the next generation of side-channel vulnerabilities?
So looking ahead, the traditional cache hierarchy, based on volatile SRAM and DRAM, is facing pressure. New memory technologies and architectures are emerging. What's on the horizon?
One major area is non-volatile memory, NVM, used as part of the memory hierarchy, potentially even as a cache level. Technologies like Intel's Optane, based on 3D XPoint, or other emerging persistent memories like resistive RAM, ReRAM, or phase change memory, PCM.
Non-volatile, meaning they keep their data even when the power's off, unlike SRAM and DRAM. How would using NVM as a cache help?
Two big potential benefits. First, eliminating cold start misses. Imagine turning on your computer and the cache is instantly warm with the data from your last session. No long initial loading penalty. Second, it could enable much more efficient, durable transactional memory. You could perform complex updates directly in this persistent cache layer, knowing they'll survive power failures instantly without complex logging.
Sounds great. Are there downsides? NVM isn't as fast as DRAM, is it? And doesn't it wear out?
Both true. NVM typically has higher latency and lower bandwidth than DRAM, and critically, most NVM technologies have limited write endurance. They can only be written to a certain number of times before wearing out. So using NVM as a cache requires sophisticated wear leveling algorithms and careful management of writes. It's not a simple drop-in replacement.
Another big trend seems to be about reducing data movement itself, because moving data burns so much energy. Near data processing.
Exactly. In large systems, just moving data from memory to the CPU and back can consume more energy than the computation itself. Near data processing tries to flip that. The idea is to move simple computations closer to where the data actually lives.
How is that implemented, like putting mini processors inside the memory chips?
Often using 3D stacked memory architectures like high bandwidth memory, HBM. HBM stacks multiple DRAM dies on top of each other, connected with high-speed vertical interconnects, TSVs, and often includes a logic die at the base. You can put small processing units or accelerators on that logic die right underneath the memory stack.
So instead of fetching gigabytes of data to the CPU just to do a simple filter or sum,
You send the command to the logic layer in the memory stack, and it performs the operation right there, only sending back the much smaller result. It dramatically reduces data movement, saving energy and potentially latency for certain types of operations common in AI, databases, and graph processing.
okay, moving from hardware changes to smarter management. We talked about replacement policies like LRU and PLRU being based on heuristics. Could AI play a role here?
Absolutely. This is a very active area of research, applying machine learning techniques to cache management. Instead of fixed rules like LRU, you could have learned replacement policies or learned prefetchers.
How would that work? Train a neural network on memory access patterns.
Essentially, yes. You train a model, like an LSTM or other sequence predictor, on vast traces of real-world memory accesses. The model learns complex, non-obvious correlations and patterns that simple heuristics like stride detection would miss. It can then predict future accesses for prefetching, or predict which line is truly the least likely to be reused for replacement more accurately.
What kind of improvements are people seeing?
Early research results are quite promising, showing potential improvements of 10% to 30% in miss rate reduction compared to state-of-the-art traditional policies on certain workloads. The main challenges are making the AI inference itself fast enough not to add latency, ensuring the models generalize well, and handling the computational cost of training and running these models. But it's a very exciting direction.
Finally, everything is moving to the cloud, to distributed systems. How does caching work when your data isn't just on one chip or one machine, but spread across a data center or even globally?
Yeah, the concept of a single coherent cache hierarchy breaks down. We move towards distributed caching systems like Memcache or Redis or software examples
Yeah.
and need scalable distributed coherence protocols.
How can you make memory access fast if it has to cross a network?
Technologies like RDMA, remote direct memory access, are key. RDMA allows one machine's network card to directly read or write memory on another machine without involving the remote CPU or OS kernel. This can bring remote memory access latencies down into the sub-10 microsecond range, still slower than local DRAM, but much faster than traditional network requests.
But maintaining coherence, that strict ordering and visibility of writes across an unreliable network sounds incredibly hard.
It's monumentally hard. You have to deal with network partitions. What if machines can't talk to each other temporarily? Node failures, potentially much higher latencies, and ensuring consistency models still hold. The simple MES state machine explodes in complexity when you try to manage it reliably across thousands of distributed nodes. Designing scalable, fault-tolerant distributed memory systems is a major ongoing challenge. Hashtag outro. So when you step back and look at it all, the data cache really is quite remarkable. It's not just fast memory. It's this incredibly complex system built on predicting the future, based on past behavior, that locality principle.
It's engineering meeting physics and economics head on, creating this vital illusion of memory that's both vast and instantaneous, even though the reality underneath that memory wall is harsh.
Exactly. It's a triumph of managing constraints, exploiting predictable patterns, and layering solutions.
We've definitely seen that layering from the basic cache line structure, the index tag offset dance, the different mapping strategies.
Through the right policies, the intricate MMUS and MoESI coherence protocols, keeping multi-core chips sane.
All the way to advanced optimizations like non-blocking caches, victim caches, prefetching, and even software techniques like tiling and cache-oblivious algorithms.
It's decades of refinement piled on top of each other.
But maybe the biggest takeaway, for me at least, is that this carefully balanced system is now under some serious stress. The security vulnerabilities show that speed came at a hidden cost.
A cost we're still paying, and performance mitigations.
And the sheer diversity of modern workloads, from AI to big data to mobile, seems to be pushing the limits of the traditional one-size-fits-all cache design.
I agree. The future probably isn't just about making existing cache designs incrementally better. It feels like we're heading towards more heterogeneous memory systems.
Mixing and matching different technologies.
Yeah, systems that intelligently combine SRAM caches with DRAM main memory, maybe NVM for capacity or persistence, maybe near data processing for specific tasks, all managed by increasingly sophisticated, perhaps AI-driven controllers.
Data placement becomes key. Not just if data is in a cache, but which cache, which type of memory is best suited for it based on how the application is actually using it. The lines between hardware and software blur.
Application-aware specialization, maybe, replacing purely generic cache designs.
So here's the thought to leave you, our listener, with. If the memory system of the future isn't just a static hierarchy, but an active, adaptive, heterogeneous entity, maybe even learning your program's behavior, how does that change how you need to think about writing software? How do you design algorithms to best exploit a memory system that's trying to anticipate your every move? Something to ponder.